My name is Shamera Chatheechan, and I'm a grade 11 student at Westlane Secondary School. This summer, I got the opportunity to participate in the Foundation of Student Science and Technology's Cooperative Education program. As part of my final project, I conducted a literature review on the solar magnetic field reversals and their implications on space weather and Earth's climate. This video will help explain some of the basic concepts of solar magnetic field reversals.
The Sun is a yellow dwarf star and is the most important star that affects our lives more than we realize. As it may just be a hot ball of glowing gases at the heart of our solar system, its influence extends far beyond the orbits of distant Neptune and Pluto. Without the Sun's intense energy and heat, there would be no life on Earth. Did you know the Sun is about 4.5 billion years old and makes up 99.8% of the mass of the entire solar system? Moving on, one of the most interesting topics to study in terms of the Sun is the solar magnetic field, which is responsible for pretty much everything, from the solar explosions that cause space weather on Earth, such as auroras, to the interplanetary magnetic field and radiation through which our spacecraft journeying around the solar system must travel. So you all are probably wondering by now, how are these solar magnetic fields created? So the Sun is basically made up of a plasma, which is churned up by the enormous heat produced by nuclear fusion at the center of the Sun. Plasma is a gas-like state of matter in which electrons and ions have separated, creating a super hot mix of charged particles. When charged particles move, they naturally create magnetic fields, and this system is known as the solar dynamo. Solar magnetic fields go under an 11-year activity cycle known as the solar cycle, and this period can differ from cycle to cycle. With every eruption, the Sun's magnetic field smooths out slightly until it reaches its simplest state. At that point, the Sun experiences what's known as a solar minimum, when solar explosions are least frequent. From that point, the Sun's magnetic field grows more complicated over time until it peaks at the solar maximum. During the solar maximum, the strong magnetic fields cool regions on the photosphere from about 6,000 degrees Celsius to 4,200 degrees Celsius, and these darkened structures are what we call sunspots. Sunspots have field strengths that are 1,000 times stronger than Earth's magnetic field and usually come in groups with two sets of spots, with one set having a positive or north field, while the other set has a negative or south field. The field is strongest in the darkest parts of the sunspot, known as the umbra, and weakest and more horizontal in the lighter part called the penumbra. At solar minimum, the field is weaker and concentrated at the poles. It's a very smooth structure that forms very few sunspots. And since sunspots are the source of mass coronal ejections and solar flares, there is very low solar activity during solar minimums. The number of sunspots varies from cycle to cycle. However, near the apex of sunspot activity, the magnetic field reverses. Thus, the next cycle begins in the opposite configuration, meaning the Sun's polar magnetic fields weaken to the point of zero and then emerge again with the opposite polarity. Although this may seem as an unusual event, this is indeed a regular part of the solar cycle. But of course, a reversal of the Sun's magnetic field is literally a huge event. The domain of the Sun's magnetic influence, also known as the heliosphere, extends billions of kilometers beyond Pluto. Changes to the field's polarity ripple all the way throughout the solar system. The heliospheric current sheet is basically a sprawling surface extending outward from the Sun's equator, where the Sun's slowly rotating magnetic field induces an electrical current. The current itself is small, only 1/10 billionth of an amp per square meter, but there's a lot of it. The amperage flows through a region of 10,000 kilometers thick and billions of kilometers wide. During field reversals, the current sheet becomes even wavier. As Earth orbits the Sun, we dip in and out of the current sheet, and transitions from one side to another can stir up stormy space weather around our planet. During the last 4 cycles, the reversal of the poles was first completed in the northern hemisphere, then in the southern hemisphere. The most notable solar cyclic influenced events occurred during the Lunar minimum and the Dalton minimum. The Lunar minimum took place from 1645 to 1715, in which sunspots were seen in less than 2% of the observed days. This period had half the level of activity as during the Dalton minimum. It was known as a Little Ice Age due to its cold temperatures. The reason studying past cycles is very important is because through the past 4 cycles, the field has been weakening. Many scientists are equating the current solar cycle 24 spotless days to that of the Dalton minimum. Cycle 23's field was 40% weaker than the past 3 sunspot minimums, and Cycle 24's level of activity is 23% lower than Cycle 23's, making it the weakest cycle in the past 100 years. Cycle 25 is expected to become even weaker and smaller in amplitude, estimated to be about 95 to 97% of Cycle 24's amplitude. Why does evolution of solar magnetic fields even matter? Well, it greatly influences climate, the 4 main impacts being changes in temperature, atmospheric density, radiation levels, and frequency and intensity of storms and coronal mass ejections. The solar wind contains structures that drive geomagnetic storms 37% of the time during maximums and only 5% of the time during a minimum. During quiet periods as the current cycle, the heliosphere's total pressure is reduced by 40%, causing coronal mass ejections to expand, resulting in a lack of solar energetic particle acceleration at high speeds. In fact, during typical quiet periods, only 1 to 3% of severe storms can be observed. This theory is evident by the 47% reduction of coronal mass ejections from cycle 23 to 24. Thus, milder space weather is forecasted for the upcoming years. Levels of irradiance can also be linked to sunspot numbers as they are proportional. There are also temperature variations like the Lunar minimum's global cooling. Scientists expect a 1.5 degrees Celsius drop, equating to temperatures during the Dalton minimum. Another impact is a decline in zonal winds and increased ozone loss below 30 kilometers. During the upcoming quieter periods, there will be fewer satellite disruptions, lower risks of spacecraft failure, and less radiation dose to astronauts, meaning a great outlook into space research. Fewer storms mean fewer destructions to oil pipelines and power distribution grids, and thus societal impacts and financial loss from solar storms will be avoided. Researchers forecast a less than 12% chance of extreme events. However, fewer impacts are not certain, as evident from past events, like during the past week cycle in July 2012, a coronal mass ejection passed Earth with a speed of 2,500 kilometers per second, and during the Dalton minimum cycle 14, a sizable group of sunspots on the southern hemisphere set off highly energetic flares, so we must continue to study the sun in order to be certain. A question that many of you may be asking yourself is, how will the lowering activity and resulting declining temperatures affect global warming? Well, studies say that there is only a 10% chance for Lunar minimum conditions to return in 50 years. These changes are very insignificant, as the irradiance levels have only varied by 0.1%, and temperature will be declining by 0.3 degrees Celsius in 2100, and the decrease is smaller than expected greenhouse gas emissions causing the warming. Thus, the lowering of solar activity cannot offset global warming.
There is still so much more to learn about the sun, and although the impacts are small, they cannot be overlooked since forecasts are still uncertain. Scientists still have many unanswered questions as to what is causing the field to weaken, and if the current conditions are similar to the Lunar minimum and Dalton minimum. And although scientists believe that the temperature decline due to the field weakening cannot offset global warming, they are still unsure and asking themselves if this information can be used to create a solution for global warming. The answers to these questions can only be found through further research and advancing technology. So stay tuned for more updates by checking reliable scientific sources and the news. Thank you for watching, and I hope this video was helpful.